Hello, folks. This section of our chapter isn't exactly associated with one particular section of your textbook, so I didn't give it a number. It grabs a little bit from 11.5 and 11.6, and of course it uses the concepts learned, from the beginning, but I just kind of titled this Logarithmic Applications. So we're going to take what we've learned so far about the algebra and apply it to, some given situations. Before I do that, I wanted to talk about a couple of different things to just kind of help you organize these thoughts in your head. Coming back from a weekend, preparing for our test this Thursday and Friday, just to kind of put some pieces of the puzzle together for you. So basically, we talk about exponential growth and exponential decay, and essentially there are four scenarios of what that graph looks like. I think the most obvious one is exponential growth. It looks something like this. It's got an asymptote at 0, and then as soon as it passes up 1, it just skyrockets up. Now, all four of these graphs will have the equation, like the standard form, y is equal to a times b to the x. And I'm not doing any shifting. I'm not going to do a minus h and a plus k. They're just going to be very, very basic graphs. So essentially what I have here is I have exponential growth. And this is a scenario where everything is positive, everything's going up. I'm going to take this graph and I'm going to reflect it over the x-axis. When I do that, I'm going to get this graph. So basically, what both of these graphs have in common, exponential growth has b, your b term is just greater than 1. Okay, so for growth, b is greater than 1. Even though this one is reflected over the x-axis, this one's shooting up, this one's going down, b is greater than 1. Now, the things that make those stand apart from each other is that because this one is going up, this is a scenario where we have a is greater than 0. A is positive, if you prefer words instead of the numbers. A is positive, and we're going to end up making our chart kind of look like this. So this A is positive is also going to go for this exponential decay graph. And then this bottom left graph here, the reason it is flipping downward is because A must be negative. Our leading coefficient is less than 0. Okay, and again, remember B stands for base. So our base has to be bigger than 1. Now, to fill in the missing pieces, exponential decay visually starts off really high and then does something like this. So essentially, it's kind of our exponential growth function, but reflected over the y-axis. Now, instead of making something positive and negative, when it flips like that, our decay function happens because our base b value is between 0 and 1. So when it's a fraction between 0 and 1, it doesn't have to be a fraction, obviously, it could be a decimal. That's where we experience that decay. So think about taking an exponent, think about taking 1/2 to an exponent, 1/2 squared, it gets smaller, right? It gets to the 1/4. And then, of course, our last graph is the combination of our exponential decay, where our base is between 0 and 1. And then if A is negative, so if our leading coefficient is negative, then it takes this graph, exponential decay graph, and it flips it over the x-axis. So these are the four scenarios and how you get each of them based on what A and B are. And I want to show you this to kind of mentally put the pieces together, and also because on Thursday on your test, I may ask you a question pertaining to exponential growth or decay in the graph or the equation, and you cannot have a graphing calculator. So you need to have the very broad sense of what these should look like. The next thing I want to help you organize in your brain are all of the formulas. So we learned 4 formulas. And what I've decided is I'm going to give you guys a question bank or a formula bank on your test. So instead of you having to memorize the formulas, I'm going to give them to you, but I'm giving them to you just as is. Here's what you're going to see on your test. You're going to see n equals n sub 0 times 1 plus r all to the t power. You're going to see n equals n sub 0 times e to the kt power. You're going to see a equals p times 1 plus r over n to the nt power. And you're going to see a is equal to p times e to the rt power. So there's going to be a bank of formulas, and this is what you're going to see. Now, though that is fantastic that you don't have to memorize them, you do have to know which one is which, like, and which scenario do you need to use each one. And in doing so, what do all of the variables stand for when you do eventually use it? So our goal right now is to help you organize this. Okay, basically, in these two equations to the left, these equations are for exponential growth and decay. Growth and decay. So, you know, that's typically things of like your bacteria population, actual population, the amount of things just growing exponentially or decaying exponentially. You'll use either of these two formulas to the left. Maybe my chart here is going to be, well, that's fine. Okay, so essentially though, the difference between the two is you're mainly going to use the top one. And again, the very popular scenario is population. The thing about the bottom equation is that usually when you have growth and decay formulas in terms of E, they are usually given to us using the problem's own parameters, if that makes sense. So we dealt with questions like that. You had one, almost your homework was one like that a couple of homeworks ago, where pretty much every word problem that I gave you, I also gave you the actual equation that you needed to go along with it. Okay, so you don't actually come up with your own. In other words, what I'm telling you is you're probably not going to use this one. And when I say probably, you're not. Okay, you will not pull this equation from the bank. If I ever ask you anything about growth or decay, you will always choose this formula. N equals n sub 0 times 1 plus r to the t power. Now, the other two deal with money. They deal with compounding interest. Interest. Okay, so these are dealing with money. Now, the main difference between these two, and I think it's going to be pretty easy to tell, is that for this first one, this top one, these are going to be for the questions where your money is compounded in times per year. Whether they use a term like quarterly or literally 12 times per year, 3 times per year, that's what N stands for, the number of times per year. The second formula is if they use the word continuously. So if your interest is just constantly less than nanoseconds at a time building on each other, then you use the compound interest equation as E on it. Okay, so this is your question bank. This is when you will use each one. If you still have questions about what all of the variables for, go back to the notes where we originally learned them, / as we do some of these examples ahead, we're going to recover that. Okay, number 1, Molly invests a sum of money in a savings account with a fixed annual interest rate of 8.28% compounded 4 times a year. After 7 years, the balance reaches $10,332.83. What was the amount of the initial investment? So again, words that stick out to me here are compounded 4 times per year. When you see this phrase, that implies that we need to use our compounded n times per year formula. So we're going to use the formula A equals P times 1 plus R over N to the NT power. Now, A is our final amount. Okay, so if A is the final amount, they give us the final amount. They say the balance, after 7 years, the balance reaches $10,332.83. So that's our final amount, is equal to P stands for your initial or your principal amount, which is what we're looking for. They said, what was the amount of the initial investment? So we're leaving P as is. That's what we're going to need to solve for. Open parentheses 1 plus R stands for the rate, 8.28%. Again, you got to make sure to take those percents move your decimal point 2 spaces to the left. So that's going to be 0.0828. Divided by n stands for the number of times a year that it's compounded, which is 4. All raised to the n times t power. Again, n is 4, and t is time, and it says that is 7 years. And then your goal is just to get p by itself. So again, just be very, very cautious typing this stuff into the calculator. Ideally, we want to simplify, the more work that you can show me, the more partial credit I can give you if you end up getting it wrong. If you just want to type stuff into the calculator all at once, like if this is all you show me and you get the right answer, then you get your credit. So it's not like I need to see a bunch, but if you want to play it on the safe side, I do like to see your intermittent calculations. For instance, I would go ahead and calculate the parentheses first. 0.80828 divided by 4, and then add 1 to that. When you do that, you get about 1.0207. Actually, I think that's an exact number, all to the 28th power. And then I would say, okay, let me actually raise 1.027 to the 28th power. So I get 10,332.83 equals p times this exponent's about 1.7748. And then obviously we're going to divide both sides by 1.7748, or again, leave that number in your calculator. We're going to try to round as little as possible throughout the problem. So when possible, excuse me, leave those numbers in your calculator and calculate with the really, really long numbers. This implies when you divide both sides by that decimal, your initial amount, or Molly's initial amount, is going to be approximately $5,000 and $5,822. I think you ended up with like 0.997 or something. So even though typically you round money to the nearest hundredth, doing so would end up rounding to both of those digits. That's why we're up to a whole number here. But typically we need to round money to the nearest hundredth. Number 2, the amount of a certain drug decreases by 30% after 1 hour of being introduced to the bloodstream. If a person takes 125 milligrams of the drug, about how much of it will be in his or her bloodstream after 3 hours? Now, this doesn't say specifically, oh, this is an exponential growth or an exponential decay type of situation, but if you look, again, it has nothing to do with money. So that kind of implies that it's a growth or decay scenario. Again, we're always going to choose this top one. You're not going to do your growth in terms of E. Okay, so we're going to do the first growth and decay formula. N equals N sub 0 times 1 plus R all to the T power. Okay, so it says how much of it will be in his or her bloodstream after 3 hours. So I'm looking for the final amount. So I've got N there is equal to, the initial amount is 125 milligrams times 1 plus the rate. This is where you have to be careful about stuff and hopefully just use your logic. It says decreases by 30%. So actually instead of adding 30%, I need to be subtracting 30%. And a lot of times, guys, our percentages are much smaller. So that's, it's usually like 0.00 or 0.0 something, but remember 30% is just 0.3. All raised to the time is after 3 hours. And then if I simplify this slightly, I get 125 times essentially 70% of the drug to the third power. And then if you calculate that, you're going to get that in as approximately, actually, anytime you get decimals that actually stop, in this case you do, and it's not a ridiculous amount after the decimal point, just give me the full exact value. Like this one is 42.875 milligrams. That's a great enough number to just write out the full thing. Now, on here, I don't really tell you how to round. Again, money is always the nearest hundredth. People is always going to be the nearest whole number. Some of you can use your common sense. Otherwise, on your study guide and on your test, I do think I specify exactly if it's a situation like this where you would need to round. Number 3, Jack invests $6,707 in a retirement account with a fixed annual interest rate of 7.43%, compounded 6 times per year. When I see that or hear that, that triggers very important information. It's going to tell us what formula we need to use. How long will it take for the account balance to reach this amount? Okay, so compounded 6 times per year. Again, you look at your compounding formulas. I have an n times per year scenario, so I'm going to be using this top right formula for compound interest. A is equal to P times 1 plus R over N, all to the NT power. So let's substitute it in our information. Your final amount is actually given to us. So this is going to be 21,859.84 is equal to our principal amount, or our initial amount is his initial investment, which is $6,707, times 1 plus R over N. R stands for the rate. We know the rate is 7.43%. So 0.0743. Divided by N stands for the number of times per year, which is 6. So this will be over 6. All to the N times T. Again, 6 is N times T is what we don't know. That's the question. How long will it take for the account to reach this amount? So this is new. We've never done this before yet. We've never had to figure out how do we get an exponent variable by itself. Well, we have, but not in a word problem context. So essentially what we're going to do is you want to isolate the term that has the exponent before, you remember when we did this last week, in order to get this exponent down, we're going to end up doing the opposite of an exponent, which is a logarithm. And we're going to do that kind of last. You want to wait until that term is isolated first. So you could do a couple of different things. You could simplify the stuff in parentheses first if you want, to where you say, okay, this is about $21,859.84 equals 6,707. You can simplify this number as 1 plus 0.0743 divided by 6, which will be about 1.0124 all to the 6t power. And then, like I said, you want to isolate your exponential term before you do the log of both sides. So let's go ahead and divide by 6,707 on both sides. And then when we do that, we're going to get about 3.259 is equal to 1.0124 all to the 6t power. Once your term, your exponential term, is isolated, there's nothing being attached to it either by addition or subtraction or multiplication, then we can go ahead and take the log or the natural log of both sides. Natural log isn't going to do anything any different than the log on this one, so I would just go ahead and take the log of both sides. Okay, so when we take the log of both sides, we have the log of 3.259 is equal to the log of 1.0124 all to the 6t power. And then our logarithm rules say, we can go ahead and simplify the left side. If you simplify this, you're going to get, actually, I'm going to leave that alone. You could figure out what this is, but again, I'm going to try to round as few times as possible. Our logarithm rules say, so we have log of 3.259, that this exponent, when you have the log of something with an exponent, that it drops out front. So it would be 6t times the log of 1.0124. And then if I want to isolate t, then I can go ahead and divide by all the stuff that's attached to t, 6 log of 1.0124 on both sides, and then I'll get my answer. Now, you got to be careful of a couple of different things. When you divide both of these terms at the same time, you have to put 6 times the log of 1.0124 in parentheses because your calculator needs to understand, like if you type all of this in at one time, your calculator needs to understand that these two are on the denominator together. Okay, so if this is what you type into your calculator, you're going to get t is equal to, and then you're going to get some sort of decimal. Again, a lot of times time, if it's talking about years, typically we'll go ahead and round to the nearest whole number, which you should get about 16. Now, I want to talk about leaving things in the calculator. Ideally, we could have done this entire problem where you input all of you don't simplify anything at all throughout, and you just kind of keep writing all of your big numbers in the log of 21,859.84 divided by log of da-da-da-da, and it would just be really, really intense and long, and we could have and maybe even should have done that, but just, I'm kind of testing you on your ability to do the algebra using those logarithm properties. So I'm okay if you're rounding, to 4 decimal places or whatever, as few times as possible throughout your problem, and I may be a little bit lenient on your decimal points on your answers if you rounded close. Again, that's the benefit of you showing your work more. If you just straight up give me an answer, you don't show me a lot in between, I can't do very much. If I can follow your work and I can see where you rounded, you're going to be just fine. Okay, number 4. The altitude of an aircraft is in part affected by the outside air pressure and can be determined by the equation H equals negative 100/9 times the log of P over B, where H is the altitude in miles, P is the air pressure outside of the aircraft, and B is the air pressure at sea level. Normally, B is equal to, this says 147 pounds per square inch. That's a lot. This should have a decimal point. Please make sure you put 14.7 PSI for B, 14.7. So this one's a double questioner. Part A, suppose the air pressure outside an airplane is 10.3 PSI. What is the altitude of the plane? So again, altitude is H. That's what we're looking for. So H equals, I'm just copying the formula here, negative 100/9 times the log of, now, P over B. P, it said, stands for the air pressure outside the aircraft. Well, that's what they give us. Suppose the air pressure outside an airplane is 10.3 PSI. So we're going to plug this in for P. 10.3 divided by B. Now, it says normally B is 14.7. So we're going to go ahead and use that given information. Question is, what is the altitude of the plane? This one, and again, I didn't even talk about this, but guys, they gave you the formula that you needed, and it has nothing to even do with E. So I know it said a lot of times your given formulas are going to be the ones in terms of E, but, sometimes I may just give you the formula that you need, and there's nothing to set up. What is the altitude? You simply just need to plug this in your calculator. Again, I'd be careful plugging in negative 100/9. Maybe putting that in parentheses if your calculator doesn't stack the fractions. And then the log of 10.3 divided by 14.7. You should end up with a height of approximately, it's round to the nearest hundredth. So you'll end up with a height of approximately 1.72 miles. Part B. If the jet's altitude is 4.3 miles above sea level, what is the air pressure outside of the jet? Now, this time it's kind of going backwards. Again, it's telling us the altitude is 4.3 miles. That's H. So instead of H equals, we're going to write 4.3 equals negative 100/9, that part stays the same, times the log of P over B. Now, the question is, what is the air pressure outside of the jet? So we're looking for P because we know that at sea level, it's 14.7. So our goal is to get P by itself. So again, even though this is not an exponential, a logarithm is an exponent. You kind of have to think about it that way. So I want to go ahead and isolate this log term first. So you can do that in think about it a couple different ways. This number out front's being multiplied, so I'm going to go ahead and divide both sides by negative 100/9. That is the same thing as multiplying by negative 9 over 100. However it is that you want to think about it and compute it is up to you. Either way, when you do that to both sides, you should end up with negative 0.387 equals, and then on the right side we're left with the log of p over 14.7. Now, you can't multiply both sides by 14.7. Even though you're dividing it right here, this stuff is stuck inside of the log. So you can't take this stuff out without taking care of the log. So when you think about your inverse operations, multiplication is division, addition is subtraction. The inverse of a log or a logarithm is an exponent, or what we've called a couple of sections ago as an antilog. So however your brain is thinking about this, you can go ahead and take the antilog of both sides. Now, an antilog, so like when I go to my next step here, on the left side I have the antilog of negative 0.387 equals, on the right hand side, an antilog of a log cancels, and we're left with just p over 14.7. An antilog, guys, if you like look in your calculator, or when you compute in calculator, we did this a couple sections ago, you literally hit second and then the log button. You're going to notice that when you hit second and the log button, it's literally 10 to the certain power. So the inverse of a log, and again, it's understood, we understand logs to have a base 10 if there's not a base written. So the inverse of taking the log of a number is having 10 raised to that number instead. So that's exactly what we're doing. So in your calculator, when you hit second log, you're going to type that in. Your calculator is actually going to be 10 to the negative 0.387 power. And you don't even have to use the antilog button. You could literally just type this in. But again, I'd like you to see the relationship there is equal to p over 14.7. And then when you do that, when you do 10 to the negative 0.387, you're going to get 0.41 equals p over 14.7. And then to get p alone, you're going to multiply both sides by 14.7. And you're going to get p, which stands for the pressure outside of the jet. And you'll get a decimal that basically, when you round it, even in a couple different ways, it'll round up to a positive 6 psi. Number 5, Kayla invests $6,964 in a savings account with a fixed annual interest rate compounded continuously. There's the important phrase. After 12 years, the balance reaches $16,131.18. So what is the interest rate of the account? So what is the interest rate? That's R. That's what we're going to be looking for. So again, compounded continuously, when you're looking at your options of the equations, we're going to be using this bottom right one. A equals PE to the RT power. A stands for the final amount, which is 16,131.18. P stands for the initial amount, which is 6,964. Times e to the, we don't know the rate. Remember, e is not a variable, by the way. E is the number. We don't know the rate, so I'm going to leave that as R. And then t is 12 years, so times 12. So again, anytime you have your variable in the exponent, the inverse of an exponential is a log or a natural log. Again, I would choose natural log here because I have e. Now, you don't have to. If you did the log of both sides, you'd still end up with the same answer. But we're going to end up, this kind of should trigger that we're going to do a natural log. But before you do that, just like we did in the other question, you want to go ahead and isolate this term first by going ahead and dividing by 6,964 on both sides. When you do that, you're going to get 2.3164 on the left side is equal to, on the right side, e to the, I'll just rearrange those, 12r power. Now, let's go ahead and take the natural log of both sides. ln. Now, when you take the natural log, on the left-hand side, we just have the natural log of 2.3164. On the right-hand side, when you have the natural log of e to the 12r power, this 12r by our logarithm rules is going to come out front. And then you can also calculate on the left-hand side the natural log of 2.3164, which will be about 0.84. And then on the right-hand side, you're going to get 12r times the natural log of e. Now, here's the benefit of doing natural log. We know that the natural log of e is 1. So then that term essentially just disappears because anything times 1 is just itself, leaving us with 0.84 equals 12r. And then to isolate r, we're going to divide both sides by 12. Leaving us with r is approximately, you're going to get it like 0.07, which again, we give rates as percentages. So move the decimal point 2 places to the right, you're going to get that r is approximately 7%. So to recap, the main questions that are a little bit different here are the ones where your variable, the unknown, is stuck in the exponent. And in order to get those exponents down, you take the log or the natural log of both sides. And again, the other big takeaway was just the organization of the formulas that are going to be given to you on the formula bank. You have to just know when you have to choose each of the formulas and what all the variables mean.